Okay, the blank PPT.
Okay, fine. No problem.
Should I read out the questions? See,
Yeah,
the questions are here also, but like nothing yet.
Yeah, you can read it out also when it comes. Welcome everyone. Harsh Makpana is here. Hope you're learning. 4 weeks over, right? Or 3 weeks over?
7th week is going on.
Okay, so that's like
Exactly in the middle of the course.
Okay, so if there are any questions, I can start. Good evening to everyone. And you have any specific questions, we will take it up. Or if you've already posted in the portal,
We can
PA
start with the one.
Pratibha will help us out. Okay.
We can start with the one that we had in the forum, like
Yeah.
why there is no way to prove
Okay.
scriptures.
See, thing is, some things are empirical. Okay. It's just that there are some underlying principle. If you take a free particle, there is no potential energy. You know the kinetic energy, and you see how the wave function satisfies an equation. From that, you deduce that it should be applicable even when there is a potential energy. Okay? So, in that sense, it's an empirical. Schrodinger equation is an empirical law, but motivated from the free particle with no potential energy. And then the potential energy is inserted. That's why I've gone through in the derivation also in the lectures. So you do have some feeling that it should be true, and then you do see tunneling, all these things in the experimental scene, that they're all consistent with this proposal. So in that sense, Schrodinger equation, even though you can say it is empirical, there are many experimental data which has been validated in the non-relativistic energy regimes. So in that sense, it's a very valid equation. Okay. So everything may not be possible to derive from first principle. Some are guided by experiments, some are guided by intuition, some are guided by the general laws, which should work in some limiting cases. And then you propose an equation and start seeing whether it's valid when you look at it from, suppose you calculate some observable quantities as expectation and the experimentalist tells you that this answer matches, then you know that you're reinforcing that your empirical law is taking care of many of the physics problems. Yeah.
Explanation on quantum tunneling.
Okay, so what is tunneling? Okay, so suppose there is this wall in this room. Okay, I cannot move out of this room, right? Why I cannot move out of this room? I have to either open the door in the wall to go out, or it's impossible for me to, because I'm also a particle, I'm also a wave. Right, Pratibha? But why cannot I move? Because I'm a wave, I should be able to move. My voice reaches the outside the wall, but not myself. Can somebody type what is the reason? That's because the wavelength is so small. The wave nature is not at all visible. Okay. Right? So my wave behavior with the wavelength is like 10 to the minus 30 some centimeter or something, which is not even visible. Okay. Experimentally, what is the range in which the waves are visible are like of the order of Armstrongs, right? That too in the microscopic physics. So macroscopic truck also has a wavelength. We can study collision of trucks also. But then there's no point in doing quantum mechanics there. You can do Newtonian mechanics. Okay. They have only particle nature. But if you take an electron, it has both particle and wave nature, and you can probe particle problem. Okay. So what happens to these particles which have both the dual natures which are experimentally detectable? They can go into a region where your kinetic energy can become negative. Okay. So this is classically forbidden. Classically, we always think that kinetic energy is P squared over 2N, right? And kinetic energy is total energy minus the potential energy. So the total energy will always be greater than the potential energy or at most equal to potential. But quantum mechanically, you can have situations where the total energy can become less than the potential. Okay? So this is allowed in quantum mechanics. And because they have both the natures, the waves can trickle into the classically forbidden region and come out, is what the theory tells. Experimentally, they also see a non-trivial amplitude or non-trivial probability of detecting it. If they put a detector outside this barrier, they do get the signal. And this principle they are using in tunnel diode. So tunneling has been experimentally observed and it is consistent with solving the Schrodinger equation where we do allow both classically allowed, which is E greater than or equal to the potential energy, or E less than potential energy, which is classically forbidden, but quantum mechanically allowed. And if you use this, the solutions, and solve them by putting boundary condition that the wave function should, at the boundaries, should be continuous, derivative of the wave function should be continuous at every boundary, you do get a non-trivial amplitude for it to be seen in a region which is classically a forbidden region, but quantum mechanically it is allowed. And if you keep a detector there, they do see the signal. Does that answer your question? I think who has asked me, I really don't know. Monday. Okay. Monday, Brown Monday. What is the difference between momentum energy in classical physics and momentum energy operators in quantum mechanics? Okay. So first of all, what we do in quantum mechanics is first we promote whatever observables you know in classical mechanics, which are position, momentum, we promote them to some kind of an operator. And whatever we want to measure, we try to find expectation values of those operators. And that gives you a number. And that number is what the experimentalist will measure. So this Ehrenfest theorem, where whatever was happening in the classical physics are all satisfied in quantum physics by the expectation value. Okay. And this is the proposal. We propose that you start with a Hilbert space, bracket. Yeah, bracket and so on. And once we have this proposal in form, we should be able to get experimentally measurable quantities by looking at expectation values of these operator formalism in these Hilbert space states. And we give it, this is what you should measure. This is what we expect, that the energy levels of the harmonic oscillator has to be discrete and equally spaced. Okay. And then how do they measure? If they see that an excited particle comes down to a ground state, it emits some radiation and that radiation frequency has to be equal to the delta E, the spacing between the two levels. It should be giving you the H cross omega, right? H cross omega from which you can extract the frequency. So these are experimentally detectable. And we have this relation. Okay. So is that answering your BIMAR? I don't know why you have all kept interesting names. I don't know. Okay, Brown was...
Before that, can we observe degeneracy in 3D box?
Oh, okay. So there's one question which got skipped. Can we observe degeneracy in the 3D box? Yes. Yes. So the wave functions, if they are unique, then if you try to write an arbitrary state, okay, suppose I say that it is degenerate, then your expectation value which you find in one state and my expectation value in some other state could be the same, right? So these things, if I want to differentiate that there is a degenerate space, I need to bring in a new observable. That observable starts seeing the difference. Okay. So how does it see the difference? Let's take the hydrogen atom. Let's take the P shell. Okay. P shell corresponds to what? N equal to 2, right? And P is L equal to 1. The states for N equal to 2 can be either S shell or the P shell. And P shell, you have degeneracy, which is 3 of them are possible. Let's not include the spin. And in the S shell, there is one possibility. Right? So N squared is 4. 4 is the degenerate states. Are you all with me, or you want me to write and show? Let's see whether I can write. Can't you?
This here. Yeah, now I can.
So N equal to 2 is 4-fold degenerate. Okay. Hydrogen atom is a 3D problem, right? So if I try to measure energy, expectation value of the energy operator, which is the Hamiltonian, in any of these states. So these states I can denote it by psi 2, 1 and m. That's one possibility. I can also have psi 2, 0, 0. That's another possibility. So if I try to find the expectation value of energy on that 2, 1m, this will be some number. Okay, so let me not write what that number is. In energy units. Suppose you do 200 E 200, then that number will be whatever you got here is the same you would get here. That's why you say it is degenerate. Then how do you know it is degenerate is the next question, right? Take some other operator like magnetic moment. Okay. So the magnetic moment will be some Bohr magneton times the LZ operator. So if I do that here, if I replace this by LZ operator, I'll get an answer 1 because L is 1, which is the P shell. In fact, I'll get 1 MH cross technically, right? LZ will pick the magnetic quantum number, right? Whereas here, if I do, I will always get it to be 0. So this way you can start probing. Are the two states one and the same? Are they actually linearly independent? If I have some other observer, if it gave me the same answer, then I can say most probably they are one and the same. If it gave you different answers, then you know that they are linearly independent. That's why there is degeneracy, because energy eigenvalues are the same. Okay? Yeah. So you can probably unshare the screen and we continue with other questions. Yes, yeah. It works here or there? Okay, what other questions are there?
Are electron, proton, and other subatomic particles spherical in shape, or it's just our way of imagination?
Okay, so for all, make it simpler, let's take it to be, they're all really tiny, of the sizes of the order of Fermi. So we can take it to be spherical in shape. I don't think that shape really matters in worrying about some of the things which we are learning in quantum mechanics at the moment. Yeah.
The question is actually why orbits are spherical in nature.
Which orbits?
Why we usually imagine electrons, atoms, or orbits in circular spherical image. The orbits in which electrons move.
Okay, so fine. So this is just a way of Bohr quantization which we do, that we take the electron which is moving around the proton, and it has to be a closed orbit. We are not really probing the nature of that orbit. So we take the orbit and then we put in the quantization condition that the angular momentum has to be quantized. And that's why you get this. It can't be anywhere, it has to be on those specific radii orbits. So I don't think it is anything more than that.
Significance of Gram-Schmidt orthogonalization.
Excellent. So Gram-Schmidt orthogonalization is a tool. Many times you will have states which are linearly independent. But the advantage, if you want to work with all these in a little neater fashion, is to make them mutually orthogonal to each other. Then things becomes a little more easy. See, for example, in the lectures, I would have said 1x squared. If you want to write any polynomial, you can use 1x squared, x cube, and write the polynomial in this variable. Instead, you can also do the Legendre polynomial, like 1x, then you have a x squared minus 1, 3 by 2 times x squared minus, those are the Legendre polynomial. If you use them, then you can use the orthonormality property, right? You know what is the orthonormality property? Oops. This one? Can I change the sheet? One more sheet, new sheet.
Discarded one. Second.
Okay. So you can have A state and B state where A, B is not equal to 0. Okay, I'm assuming that you all have been following those lectures and I've started with the Ket and Bra notation. So this is, suppose the vector space is two-dimensional, then A and B are linearly independent, but not orthogonal. Agreed? So first thing what we'll do is we'll call A to be the state 1, and to write the state 2, we subtract norm, right? So first of all, make sure that this is also normalized, and then you do this, not this, yeah, so B and then B with BL. Right? Yeah. So if you subtract this out, then what you get, and then you need to normalize it. That's what I've probably told you in the lecture. Then this 1 and 2 are very good for writing any observables in these states, because 1-2 commutator, sorry, 1-2 inner product is 0, okay, by construction. Yeah. So by construction, it will become 0. I'm not sure about this factor. Did I write it correctly? If I take A with this, sorry, there is a B state here. No, A state. I think this should be A.
This should be
This should be A.
A.
Sorry about this. I think I should.
Maybe you can on a new page. Yeah.
Stop sharing.
No, I want to put another slide. I thought it is fine, but when
The second one.
tried doing So I just said that B, and then you subtract out ABA. Sorry, this is not this. It should be this. Okay. And then you take the inner product of the element. It should be 2. So it's basically if you try and take 1 and 2 inner product, you can show that 1 is A, probably A with A because this may not be normalized. Then you can write 1, 2 inner product and show that this is B. Okay? Fine. So this Gram-Schmidt orthogonalization is useful because any arbitrary state I can write it in terms of suppose I want to write an operator A, technically I could write it as I and J, which is 1 and 2 with Ij with coefficients like Aij. Okay, so this I can do, and things are much neater to work with orthonormal basis. 1 is normalized and 2 should also be normalized. I did not do that, but you should do it. Okay. This is very important. Once this is done, then everything becomes much more handleable and easier. You do this mechanically in your coordinate system. I'm sure you all know that when you write a vector on a plane, right, it will have an x component in the x direction and y component in this one. And you know that I dot j is 0. You could have worked with some other linearly independent oblique axis. You don't work. You try to work in a condition where you can put the dot product to be 0 because then it becomes much more handleable. Working with linear independence is okay, but working with orthonormal basis makes it much more handleable and easier to see things. You can see when something is perpendicular, something is, you want to prove various things. Using this orthonormal basis is important. Even in the Cartesian coordinates in your classical physics, you always do with I, J, and K cap. Yeah.
Electron has both wave and particle nature. So can't we measure its position and momentum simultaneously when it is showing its particle nature, contradicting the Heisenberg principle?
Okay, just one. You have to stop. So let me read it. I probably was trying to unshare it.
Electron has both wave and particle nature.
Correct.
Can't we measure its momentum and position simultaneously when it is showing its particle nature, contradicting the Heisenberg's principle?
Yeah, that's exactly what everybody is trying. We want to disprove various things. Unfortunately, nature is not allowing us to do. Even in the Young's double slit experiment, people have tried to, put very, very, what do you say? It's kind of secretively, they want to see which slit it went in, and they want to see the interference pattern. Like, it's not happened. It is once you secretively try to, you are actually tampering the system. So that tampering disrupts the interference pattern because it will tell you which slit it went through. So you know the particle nature, but the wave nature gets destroyed. If you don't touch it, you don't know which slit it went through, but you see the interference. This is the way nature is. I don't have any other way of somehow getting information out of it. Yes, technically, the way we perceive things, we would like to do it. But as of now, I don't think it's been possible, at least in the quantum microscopic regime. Classical regime, yes. You say simultaneous position and velocity. That's the way you solve all your Newton's laws. Quantum mechanically, it has not happened. That trying to probe which slit it went through is trying to get information about its particle nature. If you try to do that, interference pattern on the screen just disappears. That's just the experimental. Mathematically, when we write the standard deviation for these operators, you do see that because the XP commutator is non-zero, the uncertainty in position and uncertainty in momentum is going to satisfy Heisenberg's uncertainty principle. That's the mathematics. Okay, yeah.
Why is the rest mass of photon is zero? Is there any experiment to verify that rest mass of photon is zero?
Okay, so this is a very debatable question. See, this is always independent of any course. What is the definition of zero? What is the definition of infinity? You know, so zero is what below certain cutoff we are not able to measure. If you go into a shop and ask him to weigh 2 kilos of apple or something, he will have a lowest denomination of the weighing scale, which is probably of the order of 15 grams or 50 grams. Now, digital scales also have some least count, right? If you ask him whether can I get microgram, you could probably go to a jewel shop and be able to get it. So, in some sense, it depends on the apparatus till what weight you can measure, right? So, vegetable person is not going to give microgram because for him, 10-15 grams plus or minus doesn't matter. But a jewel person may be keeping up to microgram. But if you want to say something is 0 grams, maybe it is, 10 to the power of minus 9 grams, 10 to the power of minus 15 grams. And you don't have an apparatus to say whether the mass is 10 to the minus 15. So this is what the way we will look at zeros. Okay. So in that sense, we believe that, in fact, once we were also thinking neutrinos are massless, right? There are some logical arguments by neutrino oscillations that it could have mass, small mass. But in the case of photons, standard special theory of relativity has shown it moves with velocity of light. It should have its mass, 0. But 0, can I put it to be 10 to the minus 30 or can I put it to be 10 to the minus 25 grams? These are still debatable questions. Okay? But for all practical purpose, it's not whatever apparatus you have, it is giving me 0. So it's a rest mass is 0. It's a good assumption for photons. And then we keep going. What is the actual question? Maybe I digressed a bit.
What is the rest mass? Why is the rest mass of photon is zero? Is there any experiment to verify that the rest mass of photon is zero?
Yeah. So this is what is the limit which has been put in, and there are scenarios where people are trying to take photon also has a non-zero mass but very, very small, and then there are ways in which people are trying to work with, in particle physics. These are called the symmetry breaking mechanism and so on. So let me not get into it, but for all practical purpose, you can take photon to be of rest mass and it is in a frame which is moving with velocity of light. Any particle moving with velocity of light, there is no other frame which can go faster than that, right? It is a universal. All particles which are moving with velocity of light, I cannot move faster in some other frame and overtake that frame. So there, all those particles which are moving with velocity of light, you can take it to be having rest mass. Because whatever Lorentz transformation you do in a tiny mass particle, okay, it's impossible by Lorentz transformation to make that tiny mass to become 0. In that sense, photon is in a frame moving with velocity of light and those particles have a rest mass. Yeah.
Why the Schrodinger picture and Heisenberg picture are exactly opposite of each other?
It's like the passive and the active modes which you all learn in your classical physics. You can try to write things either in the basis fixed, or you can make the basis rotate. Okay. Any observable, you fix it and make the basis rotate. So ij on a plane which was y axis is j hat and x axis is I hat. You can rotate it and make it like the basis, you can rotate it by 45 degrees so that one will be I plus j by root 2 and the other one will be I minus j by root 2. And you can work in that basis. The same observables, don't touch the observables. Or you keep the basis fixed and rotate your observables. This is very common. But none of the physics should change. You shouldn't do both. You can either do it on the state or on the operators or on the observables. Observables or states. So showed in the picture works on the states, whereas Heisenberg pictures works on the operators corresponding to observables. Both will give equivalent. In fact, I have probably proven it that both of them give you, when you do the expectation values of any of the observables, both in Heisenberg picture or showing the picture with the change, time dependent variation of the state and showing the picture and time dependent variation of the operators in the Heisenberg pictures, both will give you the same. Right? Yeah. It's just convenience. Sometimes you feel it's convenient to work with fixed basis. Sometimes you feel it's better to work with changing basis. And the changing basis is also governed by Schrodinger. Yeah.
Do you offer any internship?
Actually, this question came to me by the NPTEL office. It's just that summer I may not be around. That is the only reason why I was not sure. Ma'am, how can I send my paper to you so that you can review it for me? What paper is this?
One guy has says he has written some paper and he wants you to review it. Maybe we can.
Sure, he can do that and I'll take a look at it. What's his name? His name is like, okay, anyway, when he emails, he will let me know his actual name, then I'll. But mention that you are this NPTEL student who asked me, then I will know, I will connect. There's so many mails sometimes comes that, I kind of not able to answer many things. So if you tell me a hint that you asked me in the NPTEL, then I'll take a look at it. Yeah.
What is the reason that an atom or any subatomic particle should have mass? Why do particles have mass?
Why particles have?
Why do particles have mass? What is the reason that any atom or subatomic particle should have mass?
It's a very difficult. If everything was massless, then none of us would have existed, I think. So some are massless, some have to be having mass. Then only you start seeing interaction, collision, energy conservation, all these things, momentum conservation. I think in nature, there are massive objects which are moving with velocity less than velocity of light. There are massless objects which moves with velocity equal to velocity of light. And you need both of them to understand the universe. You do need mass. Without mass, it's impossible. Of course, there are symmetries in a system which prevents us to give mass in the beginning. But there are ways out by doing symmetry breaking by which it acquires mass. That's why the God particle Higgs particle is important, right? He was able to give masses to all the particles, electrons, W plus, W minus are the weak interacting bosons, which mediates all your beta decay. Those could be given mass indirectly by this Higgs mechanism. But for that, Higgs particle has to be seen. The theory was very neat and we expected it should be there, but only 10 years ago it has been seen.
Another person asks, what is the scope for mechanical engineers and quantum mechanics?
Okay. So this is something which I keep telling everybody that, everything has, a lot of things are changing compared to 15, 20 years ago, right? So even mechanical engineers, if you have been onto the workshop and all those engineering drawing, things have all changed. I think many places they do use some sophisticated AutoCAD way of looking at. Am I right? Whoever asked the question? You can type if you. So things are changing, and things are like, the quantum technologies, the quantum seems to be making an impact. Of course, it's making an impact in the microscopic world, but lot of ideas, it should have an impact on every other field is what I would think. Of course, for a macroscopic life, it's not that important. But if you want to see 15, 20 years ago, 20 years ago, I would say that mobile phone was a rarity. Even if the mobile phone was there, it was just for a phone call. Now people, there's an inbuilt camera, there's so many features. Right? Things are changing, and things are changing in the microscopic situations. And I feel learning like GPS is completely because of general theory of relativity, right? So I think small things which are, you may not need to know everything in general theory of relativity, but because of somebody working in that, it has had an impact in the other fields. So in that sense, I think learning this is not a harm. This is just a formalism, the way you're learning in the first course. But knowing some of these things, you may be able to see some connect in your field. That's what I would think. That's my perspective. Yeah. Yeah.
One person has a doubt regarding Heisenberg relation about E and T, energy and.
Okay, so this should be treated not exactly like the way you see X and P. Okay, so typically what happens is that when we go to relativistic situations, so when you do relativity, the first thing we learn is that space and time are not separate. Space and time are not separate. X, Y, Z and T under Lorentz transformation can mix X and T. So space-time are intertwined. So that's why people don't like to call space. They say space-time in relativistic. For the quantum mechanics course which you are doing is non-relativistic. That's why you use the kinetic energy as p squared over 2m. But in relativistic physics, there is no distinction as space and separately as time. That's one thing. So in that uniformity of notation, momentum and energy, they together form a, we call it as a 4-component vector. Okay. So just like x, y, z and t is a position 4 vector, you will have px, py, pz and e by c technically will be called as a 4-component momentum vector. If you see the kind of this uncertainty there, you do see that T and E are like X and Px, Y and Py, Z and P. That's one way of looking at it. Other thing is that when they do collision experiments, they do see some kind of a resonance. Okay? So two objects collide, they form a new particle. So when it forms a new particle and they plot this, they see a spike. The spike amplitude, whatever it is, maybe I should somewhere.
Yeah. Before that, then I'm before that.
Okay. So you can get some kind of a spike here. Some kind of a spike which you see, and then whatever is that value, let's say A is the value here, you go to A by 2. That's called half maximum. This is the maximum. And then go and see what is this width. Okay, so this is actually energy plot. And you get some kind of a width there. So if this width is narrow, okay, so those are called as the decay width. So the particle will decay, particle will remain there, the new object which is formed by collision. So in that sense, there is a kind of delta E. So this thing which you can call it as delta E, and then the lifetime. Okay, oops. Delta E and then the lifetime of the particle, they are constrained, is another way of saying it. So it's not the Heisenberg's uncertainty principle, even though, see, all the operators are functions of T, okay? So we do the Heisenberg's uncertainty for operators like X and delta P. But this should be treated in the sense that the measurement of the energy conservation, any variation, and the time period of your measurement are obeying a similar Heisenberg's uncertainty. That's the way you have to view this. Am I right, Pradeepa? That's what you all do in the particle physics, right? You look at resonance.
Exactly.
And then you look at the lifetime of the particle.
Exactly.
Right? So, yeah.
What happens if Heisenberg's uncertainty is violated in some way?
So there are a lot of theories happening already. Okay, so we say that Heisenberg's uncertainty happens in the atomic and nuclear scales. If you go to even higher, 10 to the minus 20 meters, which is beyond Fermi, we start saying that there could be the position measurement, the x component of position and the y component of position. Also, we want to say that those two cannot be measured simultaneously. Not at your atomic and nuclear scale, but even further down if you go. Okay. So a lot of new theories are there. There's something called non-commutative quantum mechanics, where delta x, delta y will have a fuzziness. You go to a coordinate system, plot a point. I know the x coordinate and y coordinate is what you would say, right? If I go to a phase space, px and x, if I want to measure and observe classical mechanics, I know x and px. But in quantum mechanics, you'll have a region. What is that region radius? Is of the order of h cross. Here also in non-commutative quantum mechanics, we say there is a region and there is some non-commutative parameter theta. This is all proposal. So far, no experimental information is available. So things can go on that the uncertainty in position momentum is not the only thing. There can be uncertainty in position x and position y also, but maybe at a very, very, very shorter distance scales, which is as at the moment not measured. Okay. So all these things are, like one undergraduate student wrote a nice article. It should be there in the archive, physics archive. You should see it. In fact, he looked at what are the new things if experimentalists can see, even in the hydrogen atom spectra, which one can come up if we use this scenario. So if anybody is interested beyond this course, you can also look at those things. Okay, yeah.
The guy who asked about internship, he is interested to have a one-to-one interaction with you at IITB when we allow him.
We will check it out with the NPTEL team and then we will get back to you. Okay.
Another question is about good books. I think that is suggested already in the slides. What is a quantum particle actually? And the second question is, what is the connection between Poisson bracket and commutator bracket? And what is the role of Planck's constant?
Yes. Planck's constant has been a universal constant which emerges whether you do black body radiation, photoelectric effect, or Compton scattering. Okay. It's not different H. It's the same H which appears everywhere. So as I showed in that phase-phase uncertainty, the H bar or H is a universal constant which gives you quantum aspects of whatever. So if you take electromagnetic field, classically it is a wave. Quantum mechanically it's a photon. Okay. So there the quantum is particle nature of waves. If you look at electron, classically I would say electron is a particle. The quantum nature of electron is a wave, de Broglie wave. Will it be a single de Broglie wave or many de Broglie waves? That decides whether you superpose all the wavelengths. If you superpose all the wavelengths, that means you allow all possible momentum, right? So precisely measuring momentum is not possible. But when you superpose all the wavelengths, it may peak, showing a localization of it to be a particle. So these are the ways in which you look at quantum nature of classically observed objects. Objects could be a wave, objects could be a particle. Electron is a particle classically. Electromagnetic field is a wave, but quantum mechanically it's the other way around. Electron is a wave, electromagnetic field, photon is a particle. Okay, so this way you should see what is quantum particle. And what was the next question?
The connection between Poisson bracket and commutator bracket.
Yeah, so this I think I've explained in the lecture that whatever you do in the quantum regime, in the limit h bar tending to 0, the Planck's constant tending to 0, you can go from quantum to classical and commutator will become like the Poisson bracket. So these are all the kind of postulates we put in and we try to match things because the boundary points should also match. All your Newtonian laws cannot become, they're also right. They're right in a different regime. If you do macroscopic objects, you don't even need to come and use Planck's constant. But if you are at the boundary where both should match, when you take h tending to 0, you have to get back your classical laws. Okay. So these are the consistency checks by which things are all very neatly done. Okay. Yeah. What else?
We have 3 minutes.
Yeah.
Are the conservation laws fundamental laws, or these are just valid because we have not seen any violation of these laws?
Okay, many processes in the lab, they do see charge conservation, they do see energy conservation, collision process, momentum conservation. So I don't think it's more than that, I think. And there are underlying principles also that you do get from first fundamental principle of charting with a Hamiltonian or a Lagrangian. You can show that the time variation of these observables are 0. So which means it's a constant of motion. So I think there is more. Hydrogen atom has rotational invariance. So you do see angular momentum is conserved, right? I don't think it is completely the way you think. It is. There is some systematic process by which you can find the conservation loss. Yeah.
What is negative resistance in tunnel diode?
I don't know what is negative resistance. I know it is classically forbidden region. I don't know the resistance becomes negative. I didn't know this. Maybe I should take a look at it. I'm not an electronics person, but I will talk to somebody and figure it out. If I know the answer, I will type it out in the live session, in the portal. I can tell Pratibha to say. Okay, so I think we are running out of time. Somebody said you would send the file for looking at it. I will take a look at it. I've seen your name here somewhere, so I will keep track of it. And regarding meeting me, I will talk to the NPTL and then we'll figure it out. We can fix a time and date and you can come and meet us. And other questions, if you have, you can put it up on the portal. And somebody asked how to score marks, right?
Yes.
Don't worry, you have to learn concepts. Marks are the last things, but if you understood the concept, you will do very well in the exams. Okay.
Anyway, we are taking the average of best 8 out of 12.
Okay, the assignments also.
Yes.
Okay, so see you then. And we'll meet again end of March again. Okay. So if you have more questions, we'll meet on 31st March, right?
Yes.
Yes, 31st March we'll meet again. Bye. Bye.
Bye.